Good afternoon, everyone. Yeah, thank you for the introduction. As said, I'm Umberto Paggi. I'm doing an industrial PhD at KU Leuven within 3D systems. So today I'm gonna introduce the link between multiple dimension and geometrical accuracy of 3D printed parts. And then I will talk about the solution to minimize downfacing distortions, specifically the zoning and the development of downfacing parameters, and the creation of offsets known as beam compensation. Then I will show the experimental setup that we use to develop these offsets, and the experimental results in a complex geometry. And finally, I will end with the conclusions and the future studies. So in the SLM process, we can characterize the melt pool with two main dimensions, which are the melt pool width and the melt pool depth. The first one is responsible for the error in the XY plane. So if we print a CAD model without any correction, the melt pool will create a part which is slightly bigger than the intended dimension. So what we can do is to shift the contour slightly inward, applying the beam compensation, and to obtain, therefore, the intended dimension. On the other side, on the Z-axis, we have the melt pool depth, which is correlated to drosses and sag defect. This is because on downfacing surfaces, we have the problem of overheating, and that's because on downfacing surface, the melt pool is actually supported by the powder bed, which has a thermal conductivity which is typically 10 times lower compared to the solid metal, and therefore we have a melt pool depth which is bigger, but also an increased amount of sintered particle and particle agglomeration on the surface, on the downfacing surfaces. Moreover, the downfacing region is subjected to different forces like gravity, capillarity, and turbulent flow, which can further decrease the accuracy of the 3D printing process. So, for example, if we use an energy density which is too high, we create a big and turbulent melt pool, which can absorb more powder than is actually intended, creating an unstable and big melt pool. Whereas if we use energy density which is too low, the capillary forces can prevent the melt pool from successfully attached to the previously printed part, and that results in pulling. In addition, after the downfacing area is scanned, we can have thermal distortion. This happens during the cooling down of the layer. So in the overhanging bit of the downfacing area, we have the downside of the layer, which is constrained by the previous layer, while the upper side of the layer is free to shrink, resulting in this angular distortion. This can build up in several layers, creating not only the problem that the part sticks out of the powder bed and can collide with the recoater, but also, and most importantly for this presentation, creating dimensional errors. So these errors are typically small, in the range of 100, maximum 200 microns. So in general, they're not relevant for big parts like the insertion mold that we've seen before, because the tolerances are high enough. But they become quite relevant for a small feature like the microchannel shown here. So if the channel is printed vertically, so this is a 500 micron in diameter. If the channel is printed vertically, we see that the circularity of the channel is extremely high and the tolerances are respected. But when we started inclining the channel, or printing it horizontally, we see that we have dross formation and deviation from the circular shape that can completely hinder the functionality of the part. So it's important to assess this distortion phenomena, and the most common way to do so is zoning and developing of down-facing parameter. What is zoning? So if in a sample geometry, we have the area above the powder bed. In this case, we have 2 layers above the powder bed, which are printed with down-facing parameter. Down-facing parameter are typically use a typically energy density which is lower compared to the middle of the part. So if we use energy density which is too high, as we seen before as well, the melt pool is going to be too big and it's going to be bigger than the CAD model intended part. But also we're going to have a fluid flow which is dripping on the previously printed part, therefore increasing the surface roughness of the product, and also decreasing again the geometrical accuracy. On the other side, if we use energy density which is too low, we can say that we are within the geometrical accuracy of the part, at least in the Z direction. But then in the XY direction, we don't reach the minimum length required for supporting the next layer. So when using optimal parameters, we obtain a surface which is homogeneous, which has minimal surface roughness, and more importantly, which is, well, theoretically, hopefully void-free. The other common solution to this down-facing defects is the beam compensation, which is an offset. So if we take a general vertical sample, we have the CAD dimension, and if we print this, as I said, I was saying before, if we print this without any compensation, we obtain a part which is slightly bigger than the CAD model. So we can measure this part, comparing to the CAD model, and calculate the offset, which is then applied to the printed contour. And then we print this new inner contour and obtain a new part, which is exactly of the dimension of the CAD model. When we're doing this on a down-facing surface, things start to be a little bit different. So if again we apply the offset, the middle offset on the whole part, we obtain this geometry. So on the sides, which are just vertical, the tolerances are respected, but on the down-facing region, we see that we create the part is slightly smaller than the CAD model, and this is for all the effects that we that I introduced at the beginning of this presentation. So once again, what we can do is to measure the part, compare it to the CAD model, and come up with a new offset, which I call down-facing offset, and apply that to the already compensated contour to print a cross section which is exactly of the dimension of the CAD model. So the total offset in the end is the vectorial sum of the middle offset and the down-facing offset. So to develop this down-facing offset, we printed one reference sample with vertical surfaces and several down-facing geometries with a down-facing angle varying from 75 to 25 degrees. This was done in titanium 6.4 with a Pro X 320 at 3D System with already optimized parameter for the down-facing region. A quick study on the residual stresses was also performed. This is a simulation tool within the 3D Expert tool provided by 3D System, so that we know that the deviation measured in these down-facing surfaces comes mainly from the down-facing region and not from shrinkage or residual stresses phenomena, which are typical of the bulk of the part. So these samples were produced, and the top surface was measured with an optical microscope. Automatic edge detection tool was used to completely eliminate the operator influence in the final results. And this is the scatter that we obtain. As you can see, the trend is not smooth. So what we did is to fit the experimental data with a quadratic polynomial fit to obtain a smooth transition from 0 to the maximal deviation registered for 30, 60, and 90 micron layer thickness. So afterwards, we applied these spin compensations to complex geometry. So we printed 3 types of channel of 1 millimeter, 0.8, and 0.6 millimeters in diameter in a horizontal direction. Half of them were compensated and half of them were non-compensated and will be used as a reference. This block, which is 1 by 1 by 1 centimeter, has been analyzed with a micro CT with these parameters, and then from this graph, from this image, the histograms of the deviation was extracted. So as you can see here, all the data are meshed together. So we cannot clearly understand which part is corresponding to this positive deviation, this negative dross deviation, or which part is corresponding to the OK area. So what we have to do is apply hypothesis. So if we take ideally smooth and flat surface, the deviation graph would look something like this, with all the surface being at 0 deviation. If we have a general rough surface, and if we consider the skewness to be 0 and kurtosis to be 3, we can then assume that the deviation scatter follow a Gaussian behavior. So this is not true, not completely true for 3D printed part, of course, but we had to start from some assumption to actually make sense of out of this whole data. So we interpolated, we fitted a Gaussian curve here in the middle, which is corresponding to with the area which is equal to the CAD model. And then we subtracted from the raw data, and the positive and negative deviation becomes much more apparent. So now we can start doing the data analysis on this graph. So on the left, we see the negative deviation, which are corresponding to the drosses. We see that in the reference channel and in the compensated channel, there is no much difference for 1 millimeter, 0.8 millimeter, and 0.6 millimeter. But that was expected because we didn't assess this problem directly. However, there is a slight improvement in all three channels, and that's because by creating a surface which more smoothly goes from 45 to 0 degrees, the area here is, in a way, it's more supported. So the dross formation happens a little bit later and therefore is a little bit smaller. On the other side, we have the positive deviation. So it's not possible in this analysis to distinguish which part of this peak is caused by this straightening effect and which part is caused by the staircase effect at the bottom of the channel. So for now, especially for the 1 millimeter sample, you see that the reduction in the positive deviation is not that high, but please keep in mind that part of this area is actually due to the staircase effect. In general, however, you see that there is a strong reduction in the positive deviation, especially for the smaller channel, which is actually completely eliminated. The final consideration that we can make is that both for the reference channel and for the compensated channel, the Gaussian peak is actually shifted, is not at 0. So the whole channel is actually slightly smaller than the CAD model. This is not surprising because the offsets were calculated on sandblasted geometries, while this channel were analyzed as built. So the internal surface is actually covered in sintered powder, which is not removed, and therefore it's obvious that the final diameter measured with the CT scan is slightly smaller than the CAD one. So in my conclusion, we managed to calculate downfacing offset on simple reference geometries and to apply it on a complex compensated geometry. The positive deviation reduction was extremely high for the smaller channels, and actually the positive deviation were almost completely eliminated in these two channels. And also we had a partial reduction in negative deviation because the dross formation was slightly less. For the future study, we will reprint we will redo the calibration part with more calibration samples. So now the downfacing beam compensation was calculated only on 5 geometry, because this is just a proof of concept study. So in the future, we will probably calibrate this this offset in a more significant sample population. And also we will apply some post-process, probably some chemical etching to the microchannel to actually get rid of the sintered powder and to see if we can achieve the CAD dimension. So yeah, this is the end of my presentation, and I will be answering your question if any.
Okay, thank you, Umberto. Are there any questions? Okay, so I will ask a question first. So if I understand well, in the compensated channels, you use special process parameters for the downfacing deviation, and you did the compensation for the shift, the lateral shift. I mean, to compensate the straightening effect. But you didn't compensate for the dross.
No. Yeah. The dross will be, well, probably actually will be assessed with Marcus. But for now, indeed, as we can see here, yeah, it's okay. It's not that clear, but every 10 degree, I compensated the channel. So from starting from half of the channel above, the channel has been printed with downfacing parameter, and every 5 degree, the beam compensation has been changed to match the downfacing calculated in the previous slide. So yeah, this is just this study is just assessing the range up to 25 degree. Below 25 degree, it's more of a overhanging structure rather than just downfacing structure. So there are all the issues involving powder, drosses and powder sintering, etc., which will be assessed later.
So you're planning to work
Yeah.
Yeah, also this spyglass that was shown, I mean, the shape was very different inside, I think.
Yeah.
Here. So is it because of different process parameters or different? Well, no, I mean the Marcus presentation of Marcus.
Marcus, that part was printed in aluminum actually, and this is titanium. So that's probably the main reason why the draws look so different. Yeah.
Any other questions? No, thank you.